Hello, hello, good afternoon, good morning, good evening, wherever you're from. Welcome to the live stream. My name is Ryan. I'm a data scientist here at KX, and today we have quite an exciting topic to get into, which is multimodal embedding models and multimodal RAG. And we have a special guest today, Frank Liu from Voyage AI. He is going to be telling us all about Voyage AI's multimodal embedding models. So, Frank, if you want to just introduce yourself real quick, that would be great.
Absolutely, would love to. First of all, I want to say thank you, Ryan, for having me on this live stream, and thank you to a lot of the members out there who are watching this as well, right? And again, doesn't matter where you are, whether it's early morning for you or sometime later in the evening. A quick introduction to myself. My name is Frank. I actually come, I come sort of more from a computer vision background, but obviously these days I think we're finding fusing a lot of that visual information or a lot of those visual semantics with text data and other modalities of data as well. Very, very important. Currently in my role, I work on applied ML here at Voyage AI, and a lot of what we do as a company is really just about figuring out the best, the way to train the best and most efficient embedding models and remakers. We do it for not just retrieval, but also for other applications as well. So they work great for all forms of semantic search. If you have something a little more, a little more traditional kind of applications such as classification or a lot of these other ones that the embeddings work great for that as well. Our models are currently available in the Voyage API or in your AWS Azure VPC or on Snowflake Cortex AI, and they will be coming to some other platforms as well. And yeah, we really have just a world-class team here. Led by a Stanford professor, and it's been we're not a super. We don't have a ton of history behind us. We've been around for maybe about a year and a half, but the space is moving very quickly, and it's great to be a part of it as well. So today I want to talk. I want to talk about. I want to talk about. We'll talk about multimodal embeddings, but what I really want to give folks, a bit of an overview of is sort of some of the classical, what we consider classical multimodal embeddings, and that is I define those as any clip-like multimodal embeddings, and also these multimodal embeddings of the future as well, right? And why do we want to, why are today's clip-like embeddings a bit of a misnomer, and why are they not really good for these multimodal retrieval or multimodal RAG applications that we're trying to build today? So just a quick refresher, and I know, maybe much of the audience here, if you're familiar or if you've been in the Gen AI space for a while now, you probably know a lot of this already. But just to get everybody caught up to speed, LLMs out of the box, they don't have access to proprietary data. So if you ask an LLM either a question that it's really not in its training set, or it's something that it really doesn't have that the relevant context or the right amount of information to answer that question, it will either hallucinate or it will tell you, hey, I don't know. So this particular, what you see on the slide here is a question about Voyage AI, right? And without retrieval, it comes up with a very, very vague sort of answer, saying that, hey, Voyage AI's mission is to advance some AI-powered solutions. But if you give it the right context, and the context I'm giving it here is context actually just directly from our website, from our documentation. If you give it the right context, it will actually give you a much, much better and more accurate response. So that is really what RAG is about, and that is why we want to build in retrieval for all of our generative AI applications, right? It makes our LLMs a lot more grounded, and also at the same time, it gives us the capability to say, hey, I can now give my LLM proprietary information and have it ask or have it answer questions and really just maybe potentially reason off of that data as well. So again, these days RAG is the predominant approach for, and RAG is short for retrieval augmented generation. It is the predominant approach for grounding your LLM with actual proper knowledge. Typically what that is like is you will add a step before generation where you actually given a corpus of data, a corpus of knowledge. This could be small, it could be something like 5, 10, 15 documents, or it could be very, very large as well. We've seen upwards of 1 billion documents, 1 billion document use cases here at Voyage. Given this corpus of documents or this corpus of knowledge and a query or a prompt, first you want to retrieve the most relevant bits and pieces of information from that corpus. give the relevant documents to your large language model, and then you get a much more grounded response, as we saw in that earlier slide. Typically, again, the retrieval step, or this green box that you see here on this particular slide, it is done with embedding models. So what happens here is that you have documents and you have queries, and given a relevant document, it will be much, much closer using either cosine or L2 or some other form of distance. It will be much, much closer in this high dimensional space than irrelevant documents. So, if we were to project these really, really high dimensional embeddings down to 3 dimensions, they might look something like what you see on the right-hand side over here, where, smaller distances just mean higher relevance, and larger distances mean lower relevance, right? So you have a prompt or you have a query and you want to find the most relevant information to potentially answer that query or to continue a conversation based off of that query/prompt. So this is what we're really looking at. And if we're to put everything together, typically you have a platform that looks like this. You have a corpus that comes in. There are some documents that gets run through a particular embedding model, maybe Voyage 3 large, or in this case, what we'll show a little bit later on is Voyage Multimodal 3. That will get stored in a vector store such as KDB. And then every time you have a prompt, you first retrieve the most relevant items from your vector store and give the results to your generative model. So that's typically what it looks like. And again, there are many variations to this. If you want to add some extra steps in between retrieval, or maybe you want to do some form of hybrid retrieval as well, right? There's a lot of different ways that you can extend this, but this is the baseline, and this really forms the foundation for all applications, all RAG applications, and really many just pure retrieval applications as well, right? If we were to drop that generative model, if we're to drop Claude or drop GPT, and we just want to do some basic form of search, right? Maybe we want to replicate, we want to do some index search over our data or over a corpus of information, and we want to be able to, let's say, find the most relevant information given some particular input. Right? We can do this. We can use pretty much the exact same architecture, only without the generative model at the end. So this is very, very, it's very, very general purpose. And as you can see, the embedding model actually forms a very, very core part of the retrieval stack. So you want a powerful embedding model, right? You want an embedding model that actually is able to put together, it's able to, in this very, very high dimensional space, it's able to really make queries and documents that are relevant closer to each other. And that's a very, very important component. So I'm going to talk a little bit about why, I call them classical, but really why most multimodal embedding models that folks are using today are actually not good for RAG. They're actually not good for retrieval. And I think it boils down to a couple of different things. But before I dive too deep into that, I want to talk firstly about the model architecture for a lot of these clip-like models. So here you see that in any instance, right, you either embed the image or the text. So clip, I'm assuming we're gonna simplify things here. We're gonna assume we're using some clip from, let's say, 2021 or 2022. It can only take image or text, right? It cannot take both. It cannot take interleaved images and texts and actually embed them together. And on top of that as well, they actually go through different trunks. So just the way that they're trained and how these clip-like models work is that they try to make the embeddings closer together towards the end. So there's not actually a whole lot of weight sharing between these two trunks as well. So there's some obvious downsides to this, right? For a lot of these clip-like models, they have lack of support for interleaved text and images, as I just mentioned. But there's also two that I think are very, very important as well, but a little bit downplayed. And the first is that there's very, very shallow text comprehension. What do I mean by that, right? And typically, a lot of these clip-like models, they have to be trained on image and text pairs. And these image and text pairs, they are pretty much, in many cases, it is very, very, there's only a very weak match between them. So, if you think about, let's say, if you go to Flickr or if you go to a popular image sharing website, and you look at the image descriptions for those images, they're generally very, very short. There's not a lot of, there's not a ton of context there. And if you really think about it, there's many different kinds of text that can match a single image, right? Depending on how descriptive you want to be. So there's very, very shallow text comprehension for a lot of these clip-like models. And to add a little bit more insult to injury, they often struggle to capture fine-grained details within the images themselves as well. So just to give you a quick example, Google's multimodal embedding, which is also clip-like. It's clip-based. They resize images to 512 by 512. Right now, if your original image is 4096 by 4096, 4K by 4K, or even higher than that, now all of a sudden you've lost a significant amount of information by doing that resizing, by doing that downsizing. There's a lot of granularity that you no longer have, or that your network no longer, or your clip network no longer has access to, right? And that is a serious. I think there's many other downsides beyond these three as well. But I would argue that, for the most part, when it comes to these retrieval applications, these three are actually the quote unquote the worst, right? These are the worst downsides when it comes to clip. There is there is one more that I want to go over that's actually a little bit less obvious though. And this is what is called the modality gap. And this is actually what prevents clip from being used, I would say, more ubiquitously. And the idea here is that irrespective of what kind of domains of data that you have, if you're matching text to any domain of data, whether it be video or images or molecular structures or even more, audio or even more complex forms of unstructured data, there's always going to be there's always going to be this fundamental property of these clip models where different embeddings from different trunks or different modalities of data, there's always separated by you can almost draw like a hyperplane between them and separate them. And this phenomenon is very pronounced when we take these high dimensional embeddings and map them down to 2 dimensions. So this is from the, I should have had a citation down here actually, but this is from the modality gap paper in 2022. And you can actually see, like, irrespective of the different types or the different modalities of data that we use, there's always some sort of gap, right? There's always some sort of separation between these modalities. And if you think about this from a retrieval perspective, that makes it really, really tough to use for anything except for cross-modal retrieval applications. What do I mean by cross-modal, right? It is good at potentially retrieving across different modalities of data. So if I want to retrieve only images given text, that is okay. But, and I'm going to go back a couple of slides here, if my corpus of data is now composed of many different modalities, now you can imagine, for example, I have some PDFs in there, right? I have some pure text and I have some audio in there as well. There's many modalities of data. Now, all of a sudden, if I use a clip-like model, depending on what I query my retrieval system with, it's going to give me only results for a particular modality of data. I know that can be a bit of it can be a bit to wrap your head around. But basically, if we just think about it from the perspective of images and text, when I do the querying, let's say I query with text, the text vectors, right? The text vectors that I query with will be much closer to irrelevant texts than they will relevant images in this high dimensional embedding space. And that is a huge problem for, quite frankly, I think pretty much every single clip-like model out there. And like I said, I think it's okay for cross-modal retrieval. So trying to retrieve between different modalities. But if we want actual proper multimodal retrieval, or we want proper multimodal RAG, this is, clip is just not going to cut it. Right? And I think in addition to a lot of those other obvious downsides there, this is a little bit of a non-obvious one. And I think this really breaks a lot of multimodal retrieval and multimodal RAG applications, right? All right, so I've talked about
Frank. No, just to interrupt you real quick with a quick question.
Sure thing. Yeah, absolutely.
Is there any limitations or advantages in the realm of context window?
Yeah, that's a great question, and I would argue no. And the reason is because even if you do have very long context, or even if you do, even let's say you have, I'm going to go back to this diagram here. You have a text trunk that, you give it a it's actually a really long context model, right? You have, 8K or 16K context length for your text trunk. Because you haven't really trained you don't really have a lot of long context image to text pairs or image to image description pairs. For a lot of those longer contexts, it ends up being a little bit less, performant.
Okay.
So you don't really see as much improvement. Now, I would say if you do have a vision trunk that also supports long context, that you can put huge images in, I do think that would make, that might make, a bit of a difference, especially if you can augment a lot of that data, with different contexts, like, different image sizes. I do think that might make a little bit of a difference. But at the end of the day, if you have, you have to have matching image and text pairs, right? And I think, simply speaking, like without, just based on a lot of the data that clip-like models are trained on, I don't think having, long context models for either of the trunks helps.
Okay.
A great question. Yeah. So I want to spend a little bit of, I've talked about all these problems about clip, right? Why you shouldn't use it in these multimodal retrieval applications. What are the obvious and the non-obvious downsides, right? Talk about the modality gap and all these other things as well. But I also want to provide, a solution, right? What is the right way to do multimodal retrieval moving forward? And here, the subsection here, I call it multimodal embeddings of the future. This is actually a bit of a misnomer, but because, these multimodal embeddings are actually available today. And quite frankly, we're not ones to really technically invent these kinds of multimodal embeddings. They've been around, with DSC and in some other forms as well. But a proper multimodal embedding model, one that does not have a lot of or any of the problems I mentioned a little bit earlier, is one that actually takes your input data, irrespective of the modality, and tokenize, turns them into tokens, whether they be visual tokens or text tokens or tokens from some other modality of data. You can imagine maybe in the future we may support audio tokens as well, or we may support tokens for video too. They take all of these and they project them directly into the network. They project them directly into the transformer encoder, and now there is dense attention between all of these individual tokens. So now all of a sudden you can think about it from this perspective. First of all, you no longer have, there's no longer separate trunks. And also at the same time, you support, interleaved text images, or if I have 10 images, or if I have 10, different documents or 10 pieces of text, now all of a sudden I can support all of those. At the same time, if I'm going to go back a couple slides to the other two downsides here, when it comes to shallow text comprehension, I'm no longer worried about that, because now I can just, when I do my pre-training, all of a sudden I can put in documents that are rich with both text and visuals. And I don't really, the fact that I'm projecting these image tokens directly into the transformer encoder means that I can now capture really fine-grained details as well, right? So for Voyage Multimodal 3 and other multimodal embeddings that are based on this kind of architecture, or based on this kind of model architecture, now all of a sudden I can give it very large images, or I can even give it let's say like very uniquely shaped images as well. So let's say I have one that is 4K by 512 pixels. I can patchify all of these and give it this kind of image as well. So I've with just a single change to the model architecture, and also to a large extent to the pre-training data, and also to some of the SFT data as well, I have resolved a ton of those problems I mentioned earlier. On top of this, you'll also see, I'm actually going to come back to this slide. You'll also see that it solves the modality gap problem too. Now, this is a experiment that some details about this particular experiment are available in the Voyage Multimodal 3 blog post, but I will describe it very quickly here. Essentially, what we've done is we've taken Voyage Multimodal 3, and we have taken, a corpus of documents, and we've split it into different ratios of screenshots, if that makes sense. So at 0.00, our full corpus is in pure text. And at 0.5, half of the corpus is pure text, and the other half is images. Now, the content of this corpus is the same, regardless of whether or not it's an image or if it's text. So the only thing that we've done is we've changed the modality of the data. And what we really want to see here is a straight line when it comes to retrieval quality. And again, we're using NDCG10 here. I'm not going to dive too deep into these retrieval metrics, but there's happy to probably that's a story for another day, or maybe a blog post for another day. But we're using NDCG10 as the retrieval metric here. It is known as the retrieval metric which best correlates with actual user behavior or user preference. And if you look at all the clip-like models, there's a very, very clear dip once we get to, as we increase the ratio of documents that are screenshots, all the way up to, I want to say that's maybe about something like 90%, right? And it comes back, sort of comes back a little bit once we get to 100%. The difference for Voyage Multimodal 3 is that it's pretty much flat. So there is no dip as we increase the ratio of documents that are screenshots at all, right? And we can see that the retrieval is very, very accurate simply throughout all of these different ratios. And that simply shows that we no longer have this modality gap problem, that this kind of multimodal embedding architecture is just simply a lot more powerful. It's a lot more flexible. And I would argue that pretty much all of the problems that we mentioned a little bit earlier with clip-like models are solved with this particular, with Voyage Multimodal 3 and with embedding models that are similar to Voyage Multimodal 3 as well. So I'm going to come back to this slide. I know I skipped over it a little bit earlier, but just a very, very quick toy retrieval example, just to show you that, hey, we can give Voyage Multimodal 3 pure text as a query. In this case, the query is strong LLMs in 2024. We can give it interleave text and images. In this case, there's in the second row that you see on the left there, we're giving it text plus a graph. We can give it multiple images as well, right? And we can, this is that third row is actually, I think that's from that's actually the ResNet paper. So that's a ResNet paper. And then the fourth row down there as well is an image plus text. So whereas in that second row, we're giving it text plus image. Now in that last row, we're giving it an image plus text, right? And you can see that it actually matches everything, if we project it all down into 2 dimensions, again, because Voyage Multimodal 3 it returns these results in very, very high dimensional embedding space. Now, all of a sudden, we have strong LLMs in 2024 matching very closely with that second row, which is actually from I think it's the Claude 3.5 Sonnet blog post. So this is the power of multimodal embeddings, right? And one trend I think that we're going to see, one trend that we've seen with LLMs is the capability for large language models getting better and better and better. And now they're really subsuming a lot of those upstream or downstream tricks that folks have to use to make them work properly, right? Things like saying, I remember, even just a couple months ago, folks were using tricks like, hey, double check your work, right? Saying, you give the LLM a problem, and then at the end of it, you tell it to double check your work twice. Just to see that hopefully, hey, maybe it doesn't hallucinate, or maybe it can correct some of its mistakes from earlier. We are doing these kinds of tricks less and less today with large language models and with generative models more broadly. And the same is going to be the case for retrieval as well. We're gonna, I think I'm not going to say that parsing is necessarily going to be, completely a thing of the past, but parsing now, parsing a document is now less relevant, is now less important than building out a proper vertical application and saying, hey, what are the best ways I can actually deliver value to my users, to my customers, to the people that I am, that I'm trying to build this application for, right? So in the retrieval space as well, not only are we seeing, hey, now we can just take screenshots of documents. We no longer have to worry about things like the modality gap. There's going to be more modalities of data that we can support moving forward. Not only are all of these true, but at the same time, I think we're also going to see, other aspects potentially being subsumed by these retrieval models as well. Maybe things like chunking, and potentially a couple of other things as well, and so on and so forth.
So do you see potentially a pretty good competition with OCR?
That's a great question. I think if you have a good parser, and depending on your application, if all you're really concerned about is that text data, you're never really going to have, it's always going to be better to run OCR first, to use Tesseract or to use some other library for OCR, and then to pass that to a pure text embedding model. But what, multimodal embedding models will continue to get stronger just as pure text embedding models will. And I think what Voyage Multimodal 3 and eventually Voyage Multimodal 4, Multimodal 5, et cetera, will give you is, really the capability to simplify your retrieval stack, right? Or to simplify the way that you do unstructured data ETL. Or just a way that you're going to be able to, you let the model try to do more of the hard work, or you let the model try to do more of the tricks rather than trying to do them yourself. I think that's a trend that we've been seeing not just for the past 2 or 3 years, but for the past 10, 20 years as well, is that we've built more and more capability. We built models that are more and more capable, both for generation, so those transformer decoder-like models, as well as for encoding or for embedding as well. So for pure transformer encoder-like models, such as Voyage Multimodal 3. Great questions, by the way. But yeah, just to wrap up real quick, I'm going to leave this slide up here for folks in case you want to scan those QR codes. Those are links to the Voyage AI Twitter and the Voyage AI LinkedIn as well. We would love to follow. Embedding quality, and really the quality of your, I would say it goes beyond just pure embedding quality, right? Just embedding model architecture as well, right? It's also a key factor for maximum RAG accuracy. And I say RAG accuracy, I also include things like retrieval or semantic search or other applications that are similar to that as well. Clip-like models, they exhibit very, very major disadvantages for multimodal RAG. And I really shouldn't even say multimodal RAG here. It's really clip-like models are only good for cross-modal retrieval. So you can really just say it's cross-modal RAG, pure cross-modal RAG. And even then, Voyage Multimodal 3 will fix a lot of the disadvantages. Not a lot. I would say they arguably fix pretty much all the disadvantages of these clip-like models, right? If Voyage Multimodal 3 like models are trained properly. So again, these are, I would say, the 3 key takeaways. Again, we would love a follow on Twitter or LinkedIn. Feel free to reach out to us. We also have a Discord as well. I'm fairly active there. We'd love to hear from you too, right? So if you have any questions about multimodal, or if you have anything, any applications or any interesting ways that you're thinking about using these models, right? We'd love to hear from you, right? I think these are always listening to, a lot of the great applications that folks are building. It's always one of the things it makes my job just much, much more fun. And I think, I always love to hear about all these unique things and challenges that folks are working on. So I want to leave it there. Would love to take some questions now, or I have a quick demo as well that I can run through for Voyage Multimodal 3. I'm fine either way, Ryan. What do you say?
Yeah, so I do have one question in the chat here.
Sounds good.
Let me put it up on the board. So is multimodal capability not available on most LLMs? And who in the market already supports the multimodal AI?
Yeah. That's actually a great point. Multimodal capability is available in most, I would say, decoder sort of models that are based on transformer decoders. So in large language models such as 4.0 or Llama 3.3 or pretty much all of the latest and greatest LLMs these days are multimodal. But when we talk about, there's a clear distinction here when we talk about multimodality versus we talk about generation. So while they are available today for a lot of these generative models, I would say Voyage Multimodal 3 is perhaps the only one on the market, the only embedding model that supports this kind of multimodal capability today. So I hope that clarifies things a little bit, right? And again, if I'm going to go to one of these earlier slides as well, I think what really helps to clarify things is maybe this one. So we're really focused on these green boxes right here, just the embedding side of things, right? How do we generate a good representation for our input data, for our input unstructured data, versus this blue stuff over here? So for a lot of the generative models that we see today, again, I mentioned a little bit earlier, 4.0, Llama 3.3, these are already multimodal, and they actually support audio in addition to images and video as well. They also support video, but I think those are those are just taking the individual frames, and also to a secondary extent taking the audio as well. For the embedding models, the only way, up to maybe about a couple months ago, before Voyage Multimodal 3 was released, the only way that people would build these multimodal RAG applications is with Clip, right? And there's just way too many downsides with Clip. And really, what I'm basically, what I'm here to say today is that Voyage Multimodal 3 is much better, and it's what you want to use moving forward. Great question.
Okay, and there was one more, wondering on your opinion on context augmented generation.
Okay. Okay. So I think there's many different flavors. I actually have a pretty strong opinion about this, which is that there's many different flavors of RAG out there.
Yeah.
And all of these different flavors, there's always a flavor of the month, right? It's like, it's like, if you remember, if you're a kid, if you ever had Jolly Ranchers, maybe like, at least for me, I never had like a favorite flavor. Maybe it would jump between watermelon and grape and et cetera, et cetera. It would come back maybe to watermelon a year later. I think RAG is, RAG is still relatively new for a lot of industries, for a lot of verticals. And I think people are always trying to chase what's new and what's hot out there. But at the end of the day, there are so many different types. There's like corrective RAG. There is there's so many that I read about it and I immediately forget about it, or like graph RAG, or all these different types of RAG. And at the end of the day, they're still based on this model that is up on the screen here, using an embedding model, or maybe potentially using some form of hybrid search as well, which I won't get into. We won't get too deep into. Combining that with a vector store. And this is the one, out of all these different types of retrieval augmented generation, all these different flavors of RAG, this is perhaps the only constant thing between all of them, is that they always have these two or these three components. And I think all these different new flavors of RAG, they're going to be popular for maybe, a month or 2 months, maybe even a little bit longer than that. But as I mentioned a little bit earlier, all of these tricks and all of these tactics to try to make RAG better, they will be subsumed into the embedding models, right? The embedding models will get better and better and better. The training data will get better and better and better. Our capabilities of, our knowledge of, what is the best way to train these will get better and better and better. And we will continue to improve on the architecture of these embedding models as well, right? So I don't think that there is a huge need for saying, hey, I'm going to really go after, this very, very unique form of RAG, unless your application really, really demands it, or unless you really need to squeeze out that extra maybe 1 or 2% performance or if you're really trying to target, you really got to get that tiny bit of performance out. I don't think it's super necessary.
Okay. And then there was just one more here. Does Voyage AI specialize on multimodal products?
Yeah, I should have made that. Great point. I should have made that a little bit clearer more at the beginning. But what we specialize in, we actually specialize more in text embedding models as well as text re-rankers. We have a lot more of those. We have domain-specific embedding models as well. So if you have, if you have finance data, or if you have law data, we specialize in those too. We do have multimodal embeddings as well, as we talked about in this particular presentation here. That is there's definitely tons of popularity when it comes to those multimodal embeddings, but it is not something that we necessarily specialize in. It is a part of our portfolio of embedding models.
All right, perfect. Oh yeah, those are all the questions. So if you did want to do that demo,
sure, and I'll run through it pretty quick. I'm gonna stop. I'm gonna see if I can stop sharing here. I'm gonna present something else. Give me one minute.
Yeah, and for anyone who has just joined, there is a comment section here. Go ahead and put your questions in, and this session will be recorded and available on the KX Systems YouTube page just when the session ends. All right.
All right. So this is I'm gonna run through this very, very quick.
Okay. Can
This
you
is
just zoom in a touch too?
Yeah, I can zoom in. How's
Yeah,
that?
yeah, that looks good.
A bit better. Yeah. So this is a public notebook. And happy to I don't know what the best way is around, but happy to share this with folks after this particular presentation as well. But this is really, we call it just a getting started with the Voyage Multimodal Embeddings notebook. And this runs on Google Colab. So the only thing that you need is a Voyage API key. So you want to go to the Voyage website, sign up for an API key. If you haven't, add it to your secret keys here, and we show you a couple of ways to do it. I'm just going to run through it. Run anyway. I'm just going to run through it, and we'll show that we'll really just show the capabilities and what you're able to do with Voyage Multimodal 3 as an embedding model, right? So first thing is to just install a couple packages. We're going to use Voyage Multimodal 3 as the underlying embedding model. And currently it is the only one that we offer, but later on we will offer more. And as we wait for all these to install, we're going to use this particular model name, and we're going to import, or we're going to make our API key available in this notebook as well. We're also just going to create a client that allows us to call the Voyage API very, very easily. So I want to show, just very, very quickly, some of a very, very simple toy example, right? And the toy example covers what I call 4 of the simplest use cases. The first is just pure text and a pure image. So, these clip-like, or maybe if I wanted to use Voyage Multimodal 3 to replace clip, what are some of the ways that we can use to do that? The other one that I'll also talk about is interleave text and images. And I'll actually show that you can do both. And you actually come up with different embeddings, but they are very, very close to each other. Again, because you can imagine if I interleave identical text and image versus interleave image plus text, it should be very close to each other, right? So let's just start with that right here. The text is going to be Voyage AI makes best-in-class embedding models or rankers. And the image I'm going to use is actually this is an image, a background image from the Voyage AI website. And now if we compile all of these into documents and we run all of these through multimodal embeddings, we can actually look at a lot. The results are already here. But we can actually look at the results of these embeddings here. And you can see that we've generated 4 vectors. Again, we haven't generated 6. We've generated 4 because Voyage Multimodal 3 supports interleave text and images. So both of these 2 and 3 will output a single embedding rather than 2 different embeddings individually. And based off of this, we can actually look at the vectors generated by 2 and 3. So again, the result is here already, but the cosine similarity between the 2 vectors from interleave data is very, very high. So this is actually quite a high cosine similarity, but it's not 1, right? It's not exactly identical, which simply shows that there is that Voyage Multimodal 3, it's taking a lot of the information that we have in the context window, and it is distilling that into an embedding, but it is not losing information about the ordering of that data, right? So the cosine similarity between these 2 vectors is still very high. And we can do, I will run through the rest of this as well, but I think this might take a while. We can do it anyway. I'm just going to run through all of it. Actually, maybe we'll just go over some of the results here. So what this second portion of the notebook here is looking at is it's taking a query, which in this case is 3D loss landscapes for different strategies, and given a data set, in this case we're using Charchive, it is trying to find the most relevant images. And the images here are from many, many different papers on arXiv that cover different topics in machine learning. And here we can see that given a query best match for 3D loss landscapes, the best match for the query 3D loss landscapes for different training strategies actually is this particular image here. And I don't remember what paper this is from, but you can see it's very, very relevant. It matches our query very, very closely. This is a loss landscape in 3 dimensions for a particular training strategy, and really just showing, I think, an improvement or when mapping down to what is effectively 3 dimensions, an improvement in what the loss landscape looks like for a particular kind of training strategy. So that's great, right? So I mean, we can already see now, like, this is a very, very powerful embedding model. We can use it for pretty much to replace clip in a lot of these different types of use cases. And I'm not going to go through this either. I do think it takes a little bit of time to run, but we can, for example, look at the capabilities for it to embed PDFs directly. So in this case, I use really seminal paper from 1953 about the structure of DNA. I can actually embed the text directly inside of the images as well. And also, last thing that I want to show, and again, I'll try to run through this pretty quickly because I know we're running a little bit short on time here, is that we can just screenshot multi-page PDFs, give all of that to Voyage Multimodal 3, and have it read or understand a lot of the context of those documents as well. So here what I'm doing is I've taken, in this particular instance, I've taken FDR's 1941 State of the Union address, and we're finding, here we can actually see all of the individual pages. And we want to try to find a particular page, a particular snippet that talks about this particular query, which is the consequences of a dictator's peace. And what we do here, we're vectorizing each individual page of the State of the Union address, and we're finding the most relevant page based off of that. And we can see here that, hey, there's a very, very relevant portion here, which is saying that no realistic American can expect from a dictator's peace, international generosity, or return of true independence, oral disarmament, or freedom of expression, yada, 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 or even good business, right? So this is a very, very relevant page when it comes to this specific query, the consequences of a dictator's peace, which is showing you that, hey, not only is Voyage Multimodal 3 capable of generating really, really strong results for pure text-to-text retrieval, but it's also capable of reading information directly inside of images, or reading text directly inside of these PDFs or these image screenshots. So it's very, very powerful multimodal model, and gives us capabilities to across a wide variety of applications.
Wow, so this might even have people start to approach chunking in a different way.
Exactly, right? You can approach chunking a little bit differently too. So now instead of chunking, let's say, instead of chunking your text with some sort of rules based or some sort of tokenization, or just saying, hey, I want maybe 10 or 20% overlap. Now all of a sudden you can just embed each individual page. Or what you can do is you can take 2 adjacent pages and embed those, and then take the next 2 adjacent pages and embed those, so on and so forth, right? And that gives you really, really strong semantic representations. It just makes your life much, much easier. Right? So you can just embed PDF. You can take screenshots of your PDFs or PowerPoints or whatever the document type that you have, and embed those directly, and have the embeddings be very, very semantically relevant. But yeah, I think this actually, a link to this particular notebook is available on the Voyage Multimodal 3 blog post. And again, if there is interest in some of the audience members today, I'll definitely figure out a way to send this out a little bit later as well.
All right. Well, thanks, Frank. That was really interesting. Definitely really insightful. Appreciate you presenting that.
Yeah. Well, I want to say thank you to all the audience members, for coming and listening to me ramble for a good 45 minutes as well. Thank you very much to Ryan, and also to some of the other folks at KX as well for having me too.
Yeah, appreciate it. So the next part of the presentation is going to be a continuation here, and we're going to talk a little bit more specifically about the RAG aspect of this, and really how they fit together in a very nice way. And just a little bit about who we are at KX. So we have a vector database called KDB.ai. And as you can imagine, that sort of fits right into this entire RAG workflow that we've been mentioning and Frank dove into. And just a quick overview of where the vector database really fits into that flow is you have your source data that you want to vectorize and potentially put into your vector database and have that entire pipeline for you from a RAG aspect. But you start with that, and it could be a variety of different modalities, just like Rag mentioned. It could be audio transcriptions, PDFs, text, images, even video. And you run that through your multimodal embedding model, where that is all vectorized in the same vector space, which is great. And then you can insert that and store it in your vector database. Now, the power here is that you can do a very efficient and fast similarity search against a large amount of data with a vector database. And this will allow you to search through all your data, find the most semantically relevant data using those vectors embeddings, and then it will retrieve that data for you. And then you can pass that on to sort of whatever downstream application you want. So, of course, the big one is RAG, but there's a variety of other use cases that are available for vector databases as well. So some of the other use cases, just like document search, things like sentiment analysis, pattern matching, and outlier detection. We have a really interesting notebook on our GitHub about image similarity search. So that's really a fun one to look into. Of course, retrieval augmented generation, hybrid search, where you're combining your keyword search and BM25 searches with your dense vector search. And then we also have something called temporal similarity search, which works with time series data. And I'll touch on that just a little bit in a moment here. But the point is, a vector database has a variety of different use cases, including RAG, but plenty others as well. So, this sort of brings up the question, like, why would I want to use a vector database, and why would I want to use KDB AI when, really there's vector indexes out there, like FIs, for example, that are free and relatively easy to use. But when you start thinking about some of the features that are included in a vector database and the scale that you can achieve with a vector database, really, if you're thinking seriously about moving an application like this into production, a vector database would be necessary for that, especially at a certain scale. So there's a few different features that KDB AI, the vector database, does offer that will improve your life and make things a little bit easier. So first of all, KDB AI has a variety of different vector indexes available. And an index is just a data structure that allows you to store data in an efficient way and make retrieval as fast as possible. There's several different types of indexes, but KDB AI actually allows you to do in-memory indexes or on-disk indexes. So it has both options. And the typical vector index is in memory, and that works great and it's fast. But as soon as you're in a memory-constrained environment, or you have a larger data set, that can be quite costly to store just all your vectors in memory. So having an on-disk option is one good method to sort of approach that problem. Secondly, the database does include partitioning, so that will help you scale up all the amount of vectors that you can hold in your vector database. There's really good metadata filtering as well as fuzzy filtering on metadata fields. So this is sort of a unique and interesting feature here where metadata filtering will help speed up your vector search by shrinking that search space. So you're only searching across vectors that meet that specific filter that you set. But fuzzy filtering is where you're able to actually handle typos or like international spelling variation within the metadata fields as well. And I know at a past project I worked on in the manufacturing field, there were several metadata fields that had been entered by humans over the course of several years. And there were tons of spelling errors and typos in there. And thinking back, I wish we had that fuzzy filtering capability in the database that we were using. It would have made life a whole lot easier. And then finally, we have something for time series data. So yeah, you can handle all your multimodal, unstructured data, text and images and all that sort of data. But with KDB AI, you can actually also use structured and time series data and do pattern matching on that data. So if you wanted to go back and find similar patterns, when did this pattern occur in the past over, millions of different time series windows. You can do that. You can do levels of anomaly detection with this methodology as well. So if you're interested in that, that's sort of a whole different topic, but there's several videos on our YouTube channel and notebooks on our GitHub that will explore how you can use this to help out your time series analysis. And then there's just a variety of other features like multi-index search and hybrid search. So again, that keyword search mixed with your dense vector searches. And then you can create multiple databases that contain tables and multiple indexes within them. So there's a ton of flexibility here. But what is really interesting about all this stuff is that this is all included in the starter edition for free. And you can go and sign up for that right now at kdb.ai. This is awesome because you can create a vector database that holds millions of vectors for free. And those vectors and your data will not be deleted unless you are not active for over a month. So we have a lot of different options to get started with that, including a cloud version, a server version if you want to host on your own infrastructure, or using one of the cloud providers, you can do that as well. I personally recommend just start out with the cloud. I think it works quite well. You can go ahead and go to kdb.ai and click sign up. And when you sign up for your cloud instance, you will get a 4 gigabytes of memory in your instance and 30 gigs of storage right up front. So, this isn't necessarily just for like getting started POCs. I mean, you definitely come here and kick the tires, but there's enough capability here where you could, potentially take even the starter edition into production. So if you do want to sign up, just go to KDB.ai. You can sign up, fill out your email. You'll get a confirmation email. You can use your Google account as well. And then once you get in, you will go ahead and go to the connection details tab. Go ahead and find your endpoint and your API key, and that's all you have to do. So now you're set to go. You have access to your vector database, and you can get started with several different sample applications. We're going to be going through one here in a moment on Multimodal RAG, and there's a ton of other sample applications in there as well, including working with like lane chain and llama index, a different RAG, even the time series analysis stuff. So plenty of material for you to get started with. And one of the other things that we want to make sure is that your developer experience is great. And so not only offering the free starter edition, but we have an academy that has video lessons for free that will walk you through all the different elements of the vector database. We have a Slack channel. Definitely encourage you to join that. We have a learning hub and GitHub and YouTube that has all sorts of information to help you understand vector databases and generative AI topics like RAG even better. So with that, I'm just going to present like 2 slides here, and then we're going to get into some code. I know we just have a few minutes left, but that is no problem. Frank did a really good job of covering a lot of these concepts already. But what I want to talk a little bit about is where KDB.ai, the vector database, fits into this entire pipeline here. And you have your data, you send that through your multimodal embedding model, where then you get your embedding. So this is what Frank talked about. You get your multimodal embeddings for whatever type of data that you have, images and text, for example, and then you can store those embeddings in KDB.ai. You get all the benefits that we just talked about, as well as the ability to then take your user's prompt, and that could be a variety of different modalities, including text or an image even, embed that with the Voyage AI multimodal model, and then you can do semantic search upon your vector database. So what this does is it then identifies what is the most semantically relevant vectors, what are the most semantically relevant vectors to the user's prompt. It will retrieve those for you, where then you can pass that to your large language model and generate a response. So it's naive RAG. There's plenty of ways you can optimize this, just like the context retrieval augmented generation. That's a potential way to optimize this pipeline. And there's a ton of ways to optimize this, and that's really an entire session on its own. So maybe if you're interested in that, let me know in the comments, and we can make RAG optimization a topic for an upcoming live stream. And then after we are passing this to our large language model, we do want to just ensure that we're using the right type of large language model. So this actually was a question I was just asked. You want a large language model that ideally can handle images and text directly. So if you have that, this is great. You just pass your extracted information, your retrieved information to the LLM and get your response. But if you are working with a text-based LLM, you would then just have to transform all of your data into a text format. So like if you had images, for example, you could get a text summary of those images and then pass those to the LLM. Ideally, and what we're going to show in the demo just in a moment, is using a multimodal LLM that can handle the multiple types of data. All right, so let us jump into some code, and we just have a few minutes, so I'm not going to run this. I ran it earlier, but if you want to run this yourself, you absolutely can. It's on our GitHub. And what we're going to do here is build a multimodal RAG pipeline. And what we're going to do is do it in a very simple way that you can sort of take, understand, and then apply it to your own use case. So the setup is relatively simple. We're just going to be doing multimodal RAG on images of animals, like this bat, for example, and descriptions of those animals in text format. So as you can imagine, this is really just a toy use case, but this pipeline really remains consistent regardless of the use case, aside from obviously some optimizations that you can make to it. But my hope is that you will see this, you can try this out for yourself, and then transform it for your own use case. So walking through this notebook, you can go ahead and pip install all of your dependencies, do your imports, and then define the model that we're going to be using, which is the Voyage AI Multimodal 3 model that we just talked about. We go ahead, we'll put in our API key and set that environment variable. The next thing that we'll do is download the images and text. Now this is Colab, so it makes it super easy for you to just go to this notebook and run it yourself. So all this is doing is reaching out to GitHub and downloading all those texts and images that we have on our GitHub, which is a bunch of images of animals and their corresponding text descriptions. So now that we have our data downloaded, all we can do is set up a couple helper functions to read text from files, to go ahead and actually transform our data into embeddings, or get the embeddings from passing our data to that multimodal embedding model. And then the same thing for our query. When we pass our query to this function, it'll get a embedding format of our query. We'll go ahead, create a data frame that will hold all of the data. And then this is the same data frame that we'll use to actually ingest the data into our vector database. So we just create an empty data frame here. We go ahead and get the path for our images and text that we downloaded earlier. And then we can go ahead and generate our multimodal embeddings. So all we're doing here is just iterating through the images and the text, and then we're passing that to our embedding model to get all of the embeddings for all of our images and text. We then put that all together, and we get a data frame that contains the path to our image or text, the type of media, whether it's an image or text, and the corresponding embeddings for each of these. So at this point, we have the data we need. We have our files and our data embedded by multimodal embedding model. And now we need to set up the rest of our RAG pipeline by inserting this data into the vector database. So to do this, we set up KDB AI, and we just do our KDB AI imports, put in our API and endpoint, which you can go ahead and grab on kdb.ai. Pretty easy to sign up there and get that information. And then we connect to the session and go ahead and connect to a database. So when you get your KDB AI session, you will have access to a default database that you can use. You can create other databases as well, but in this instance, we will just go ahead and use that default database. We'll define our table schema. So that just means what are the columns that we will have in our database. And of course, they'll be similar to the data frame that we just instantiated earlier. We'll have our path, which contains a string. We'll have our media type, which contains a string. And then we'll have our embeddings. So this is the magic field right here where the embeddings are held. And this is the field where we will define our vector index. So remember, the index makes search much more efficient and much faster, which is really beneficial for when you're working with larger data sets. Now we define the index that we use as just a flat index. In this case, I'm showing the Q flat index, which is our on-disk version of a flat index. But there's other options too. Like if you wanted to just use a flat index in memory, you could use QHNSW, which is HNSW on disk, HNSW, IBFPQ, a variety of different indexing options that you have. And then we say, hey, we're going to apply this index to that embeddings column from above. So at this point, we will then create this table given the schema and the index that we just defined, and we will insert our data into the table. So once we insert our data here, we can query our table and see all of our data was inserted successfully into the table. And now we are ready to do the retrieval phase of our RAG pipeline. So we can go out and actually perform a similarity search on our data. So let's give it a shot. We'll create some helper functions just to view our results to make it nice and human readable for us, and then a function that actually goes ahead and does the actual search on our vector database. So let's start with a query, brown animal with antlers. Let's just see how it does. I know that we have a deer entry in our data, so let's see what happens. Print out the query vector just to see the embedding that was created by the query here. And then when we perform that search, we see that we're actually retrieved the correct information, which is 2 pictures of a deer and a description of deer. So these are all of the deer data that's in our database, and we were successfully able to retrieve that. So now let's try one more query here. Green and yellow insect that cocoons. Okay, well, it looks like we were successfully able to retrieve a couple pictures of caterpillars and a text description of caterpillars. So our retrieval seems to be working quite well. And now let's complete the RAG pipeline here, and let's pass this information to a multimodal large language model and ask some questions about our data. Now in this case, we'll just use Gemini, and you'll do your pip installs, pass in your API key, set your environment variable. And we're using Gemini 1.5 Flash. I think there's an updated one, Gemini 2.0, you could try as well. We just create a helper function that will just set up our data to be passed to the large language model. We'll create our prompt. What can you tell me about the caterpillars in the images? What species are they? And then we will basically pass this prompt along with our retrieved data into Gemini. So this is the point where we're about to begin generation. So if we execute this, we're passing that information to Gemini, and Gemini is responding to us and giving us descriptions of what it is seeing in these images, saying the first image shows a hairy caterpillar with dark segments and kind of describes what it sees and makes a guess about what type of caterpillar it is. And it does the same for the second image. So this is, I guess, naive RAG, multimodal RAG in a nutshell. And, I think it's a simple use case here, but really I think it's easy to follow where you could take your own use case, your own data, and sort of plug it in here with a few minor adjustments and be able to start experimentation rather quickly. So I hope this was helpful. And if you have any questions, again, feel free to put it in the chat. And also, we are on, both Frank and I, we're on LinkedIn. So feel free to connect with us and join the Slack channel with any questions as well. All right, let's see if we had any questions come in the chat here. Are we also on AWS? So right now we are on Azure, but you can actually deploy the Docker container on whatever cloud provider that you want. So if you wanted to try the server version, you can deploy it. It's just a Docker container, deploy it wherever you want to deploy it. So, all right, let's see. I think that looks like all the questions here. So we can go ahead and conclude the session. Frank, just really appreciate you coming. I thought the presentation you gave was really interesting and learned quite a bit from it. So thanks a lot for that.
Thank you for having me. Appreciate it.
Yeah, and thanks everyone for joining. We both appreciate your time a lot. Again, connect with us. We're happy to chat. This is this is a really interesting space that's moving very quickly. So But yeah, let's get it going. And we will keep you guys updated. Check on my LinkedIn and on the KX page for the next live streams. There'll be some upcoming live streams and whatnot. So thanks again and have a great day.
Thanks, everyone.